Hello, in this video we are going to study about CPU, the central processing unit. We will be studying the introduction and then we will be seeing the types of CPU organizations, and we will see the detail of single accumulator organization and the general register organization. What is a CPU? CPU is that part of the computer which performs all the data processing. All the operations within the computer are done by the CPU. These are the major components of a CPU. There is a control unit, there is a register set, and we have a ALU. What does register set do? Register set stores all the data which we use in an instruction. ALU performs all the micro operations for the execution of the instructions. And control unit, what does control unit do? Control unit supervises the transfer of information among the registers and instruct the ALU as to which operation is to be performed. So there are three types of CPU organizations. The first one is single accumulator organization. In a single accumulator organization, we have one address instruction. What does one address instruction mean? Let's see the format of an instruction first. This is the mode, this is the opcode, and this is the operand. So we want to perform an operation on an operand. So this operand can be 1, 2 or 3. So if there is one operand, it is known as single operand. And how does this connect to one address instruction? So we have a command. Let's assume we have a command of an instruction as INCA. So what does INCA do? INCA means we are incrementing the value of accumulator by 1. Similarly, if we have addx, this means we are adding the value into accumulator. Which value? The value at memory address x. So because one address is being used here, this part is the one address of memory, and in this one we don't have any memory location being used. This is the accumulator. So in single accumulator organization, either we have 0 addresses or we have one address. Similarly, in general register organization, what do we have? We have an ALU, we have multiple registers. Suppose this is R1, R2 and R3. Now I want to add R1, R2, R3. So what will happen? In R1, the addition of R2 and R3 will come. So in this we are using 3 registers. Some people use same code using 2 registers. How can we do it? Add R1, R2, or we can write here x, R1, or we can write here x, y. So x and y are the memory locations, R1 and R2 are the registers. So here we have 2 registers, here we have one memory, one register, and here we have 2 memory locations. So So using these three registers or the two registers, we have this register organization. Okay. In stack organization, what do we have? We have a stack. Suppose we have this, all the registers are in a stack. So we have one top of the stack variable. Along with that, we can use push and pop operations. Push and pop. How do they work? If I say push x and x is pushed here, similarly we push y, y will be put here, and then we use this pop at this place. This pop will help us put the y variable into the top of the stack. Or we can also use this as push x, push y, and then add. What will this add to? This will add these two variables x plus y and update the stack as x plus y. This add instruction does not have any address in it, but this push x and push y are using two addresses from the memory. So x and y means there is a memory where x is this location, y is this location. So this x will be used as m of x and this y will be used as m of y. These values will be put into the stack. When we will add, the values will be added and this location will be filled with x plus y. Now let's see what does single accumulator organization mean. Earlier computers had accumulator based CPU. In this type of CPU organization, the accumulator register is used implicitly for processing all the instructions of a program and store the results into the accumulator. So this instruction format is also known as one address field. So the instruction format that is used by this CPU organization is one address field. Due to this, CPU is known as one address machine. So following are the features of single accumulator based CPU organization. In this CPU organization, the first ALU operand is always stored into the accumulator and the second operand is present either in the register or in the memory. And accumulator is the default address. Thus, after data manipulation, the results are stored into the accumulator. One address instruction is used in this type of organization. AddX means we are adding into the accumulator the value at memory X. INCA means we are incrementing the accumulator. Let's understand general register organization. Why do we use processor registers? When the instructions are executed, memory locations are needed for storing the pointers, counters, return address, temporary results, and the partial products. And because of all this, by accessing memory again and again, we will be wasting our time because memory accesses are the most time consuming operations. So there is another way. We can add few registers into the machine and we can use these intermediate values, all the values of pointers, counters, etc. in the processor registers. Now CPU bus system with common ALU. When a large number of registers are included in a CPU, it is more efficient to connect them through a common bus system. So we need a bus to connect the registers. Since the registers communicate with each other not only for the direct data transfer but also while the performance of the various micro operations, it is necessary to provide a common unit that can perform all the necessary arithmetic, logical and the shift micro operations in the processor. See this diagram carefully. So initially what happens is, suppose I want to add values of R2 and R3. This R2 and R3 needs to be added and to be sent into R1. So what I want to do is R2 plus R3 result should be sent to R1. How will we do it? Now there are multiple registers here. All of them will send the value to these mux A and mux B. I want to select R2 and R3 only. How will I do it? So these are the values. These 7 registers send their values to these multiplexers. The value of selection line A will decide which register value needs to be accepted. So if I want to accept R2, I will pass here 010. This 010 will help R2 to give the value to bus A, and similarly this selection B line will help in selecting which register value need to be passed to the B bus. So I want to pass R3, so it should be 011. Once these two buses get their values, ALU will perform the addition. Now this OPR means these 5 bits are being used to decide which operation needs to be done. So we want to use the plus operation. So this ALU will do the summation of R2 and R3. This will pass the output to this line, and this line will be available for all the registers. Now I want to send the result into the R1. So R1 will be selected using this selection line D decoder. So the value will be 001. When selection line D will have the value 001, the result will be passed into the R1 and the work will be done. So selection A line is using 3 bits. These are the 3 bits. Selection line B is similarly using 3 bits. Selection line D is using 3 bits, and operations of the ALU are taking 5 bits. Total is 14 bits. Let's see more detail about this. Now this is the detail written what I have already explained. Output of each register is connected to 2 multiplexers to form 2 buses A and B. Selection lines in each multiplexer select a particular register or the input line for the particular bus. Buses A and B form the input to the ALU, which based on the operation selected by OPR performs the desired microoperation. The result generated by the ALU is available for output data. It also goes into the inputs of all registers. The register that receives the data from the output bus is selected by a decoder with the help of the selection line D. So suppose we want to do the summation of R2 and R3 and send to R1. What we have to do is, selection line A will help in selecting R2. Selection line B will help in selecting R3. So these two values will be sent into the bus A and bus B. ALU operation selector. So this operation we want to do is addition, and the decoder destination selector helps in transferring the content of the output bus into the R1. At the beginning of the clock cycle, there are 4 selection variables: selection line A, selection line B, selection line D, and OPR operation. These are generated in the control unit. During the clock interval, what happens is R2 and R3 propagates through the multiplexers to the output bus and into the destination register. At the next clock transition, the binary information from the output bus is transferred into the destination register R1. Let's see the detail of control word now. I told you the control word is 14 bits long. First 3 bits are for selection line A, second, third bit are for selection line B, then the 3 bits are for selection line D, then 5 bits are for OPR, operation done by the ALU. So these are the selection line A, B and selection line D. These 3 bits will help in selecting what work has to be done. So 010 means R2 is selected for selection line B, A or D. For instance, if selection line A is 001, so it means R1 is selected. When selection line B is 100, it means R4 is selected. So we have R1 and R4 which are selected, and selection line D means selection line D 110 means R6. So the destination is R6 and we will be using R1 and R4 for some operation. When selection line A or B is 0, the corresponding multiplexer selects the external input data. Input is given externally. When selection line D is 0, no destination register is selected. The content of the output bus are available in the external output. So all these 3 values are handled externally when values are 000. So these are the 5 bits. If all 5 bits are 0, we want to transfer A. When all 5 bits are 00001, then we want to increment A. This symbol should be TSFA. So these 5 values of the OPR will help us select which operation we want to do. So suppose we want to apply this operation R2 minus R3 and result into R1. So R2 is selected through 010, R3 is selected through 011, R1 is selected through 001 and subtraction is selected through 00101. So subtraction is 00101. So these 14 values in the control word will get this work done. Similarly, multiple microoperations can be done using these control words. So what is control memory? Till now we have seen that many microoperations can be generated in the CPU. The most efficient way to generate control words with a large number of bits is to store all of them in a memory unit. A memory unit that stores control words is referred to as control memory. Now by reading the consecutive control words from control memory, it is possible to initiate the desired sequence of microoperations for the CPU. This type of control is referred to as microprogrammed control. Thank you for watching this.